In this video, I would like to cover a really important topic for this course, which is the discretization of states, continuous time state space equation. Technically, we will do the same thing that we did using the Z-domain and S-domain approach. Okay, so we will approach the problem from the same perspective. Let's assume that we have U of K, which is a discrete time input. Okay, we have a zero hold produces U of T, okay, which is the actual input for the plant. So we have a state space dynamical system, AX plus BU, Y is equal to CX plus DU. So we have Y, and also we have states X, okay? And what we will try to do that, so under this assumption, we will sample the states, okay? So technically these are X, okay? So we will sample all of the states using the same idea, like uniform sample, and we have X of K. So this is the basic structure, and we will try directly formulate the problem from the perspective of state space. Okay, let's clean that and write it mathematically. Okay, good. Okay, so nice. So let's write it here. So X dot is equal to AX plus du. We have Y is equal to CX plus du. The most important part, of course, is the state evolution equation. Okay, so given that we have a zero order Hall kind of input, we know that U of T can be written as U of K for the interval of when T is equal to KT, K plus 1T. Okay, in between one sample interval, our input is constant. Okay, so this is the main assumption because it comes from zero order Hall operation. Okay, so under this assumption, we will start with the general solution, time domain solution of a state space approach. Okay, we know that X of T can be written as e to the power AT, okay, X of 0, which is the initial condition, plus 0 to T, e to the power A, T minus tau, B, U tau, D tau. Okay, good. So we know that. So what we can do is, so we can technically do it from T0 or 0 or from any time interval. So what I can do instead, I can replace 0 with T0, okay, and here 0 with T0. That's great. Okay, so everything is safe. And we know that, of course, T is greater than T0. Okay, now let's assume that T0 is equal to KT. Okay, so K instant in the sampling. And T is equal to, okay, K plus 1T. So what are we trying to do is mapping from KT to K plus 1T, or one sample interval, which is the important part for us in the discretization process. Okay, so let's do that. This is equal to X, KT. Okay, so let's write it better. Okay, that's great. X, KT is equal to, no, let's say K plus 1 because I'm just mapping it. So let's change the K. X, K plus 1, T is equal to e to the power A. Okay, so and this should be, sorry for that, T minus T0. Okay, that's great, that's important. A times T times X, K, T. That's good, okay. So plus from KT to, okay, so here K plus 1T, e to the power A, I'm just replacing everything, K plus 1T minus tau, B times U tau, D tau. Okay, but important thing is, what's U tau? Okay, U tau is U of T from K of T to K plus 1T, and we know that it is constant. So why I can do that, I can modify this, D tau times U of K, and this is in parentheses. Okay, so we simplified the problem a lot because now input is outside of the integral. Okay, it's pretty easy now from this perspective. Okay, and we technically simplified even further, not simplified, but clarify the notation in the sense that this is equal to x k plus 1, okay, e to the power a t x of k plus, this is the same, kt k plus 1 t e to the power a k plus 1 t minus tau b d tau, and of course we have u of k here. So now we have a, like, if we compute the integral, which can, of course, we have a like more discrete time relation. So xk plus 1 is a function of x of k and u of k, and this is what we want from a discretized state space representation. Okay, now I will do something else. Okay, so let's clean here such that we can see the results. Okay, I will do some change of coordinates. Okay, that's great. It's the object razor. Yes, it's object razor. So let's use it. This is even faster. Okay, I figured out that at the end of the semester. Okay, good. So let's do some change of coordinates. Okay, let lambda is equal to k plus 1 t minus tau. And of course, we are just doing it for the perspective of the integral. We don't need to change anything outside the integral. Okay, then what we can do is, this is same x k plus 1, that's great, e to the power a t x of k, and as I can see that this is the most important part anyway, plus what's that? Okay, so if I just look at that, let's look at the outside later. This is equal to e to the power, okay, sorry for that. Okay, e to the power, okay, this is technically lambda, which is great, a times lambda, I really simplify things, times b. Okay, so what is d tau? It is minus d lambda, because I need to iterate that. We have u of k, of course, here. So what we should write at the bottom. Okay, so when tau is equal to 0, okay, no, when tau is equal to k plus t, so lambda is equal to k plus 1 t minus kt. That's great. I think this is equal to kt, right? Kt, that's great. When tau is equal to k plus 1 tau, lambda is equal to 0, so we have 0 here. That's going somewhere nice. Okay, so we have from kt to 0, we have any integral limits, we have any variable, but we have minus here, just changing to the plus. Okay, so this is the lambda. Let's clean it here. Okay, so it's not kt, it's technically just t. Okay, sorry for that. It should be t, just a. Okay, exactly, it's t. Okay, so if I change the limits, I will find that this is equal to t and this is equal to 0. Okay, that's great, right? Everything seems to be very nice at this point. So this is an integral, right? If I know e to power a, okay, it's a matrix function, okay, and I also know that I can just pop up b outside, d lambda. I can also just keep it inside, it doesn't have a problem. If I compute it, that's what I have is x of k plus 1 is equal to a matrix times the states plus a matrix times b times u, or this is also a matrix. So if you remember, I can clean this because I don't need that. I can clean this. Okay, x of k plus 1 is, if you remember the classical discrete time state space approach, we write it in this form. X of k plus h times u of k. But as you can see, I already computed that. So what is G? So discretized system matrix is equal to e to the power a capital T, which is the sampling time, and discretized input matrix H is equal to 0 to t e to the power a lambda, the lambda times b. Okay, so e to the power a is a like function matrix form, and it's generally easy to compute the if you know already e to the power a as a function of any variable, the integral is not that hard. Okay, so how you can compute G is very easy. It's simply compute the state design transition matrix. Instead of small t, use the capital D, sampling time. This is generally easier one, and this is the most important part because it's the fundamental matrix that defines the state evolution equation. Of course, input matrix is important. B is nice, so we have an integral. Okay, sometimes you may have to use this integral form. Okay, so it may be inevitable. You can just use the integral, but sometimes it can be even easier. Okay, so when A, okay, determinant of A is not equal to 0, when A is invertible, okay, which means that there is no 0 eigenvalue in A, H can be simply written as a to the power minus 1 e to the power at minus I times b, or it's also equal to e to the power at minus I times a to the power minus 1, so a inverse times b. Okay, so if you know a, if you know e to the power at, if you know, of course, identity matrix, computation of this is super easy, especially if you are using MATLAB or other kind of computational tools. Okay, so I generally have to prove of this in the mini projects, which I can do, which is not that hard because it's coming from the properties of a to the power at, so matrix exponential. Okay, so we already computed G and H, and now let's compute the output equation, right? Okay, let's start with that. So in the output equation of the continuous time system, we have y of t, c of x of t plus d of u of t, and what we are interested in is in the sampled output. Okay, so what is yk of t, which is equal to yk, we know that, is equal to, just sample the signals, right? X of kt plus d of ukt. As you can see, it's super easy. So y of k is equal to inted is equal to c times x of k plus d times u of k. Okay, this is super great because it means that output equations C and D matrices is same with the original plans C and D matrix. You don't need to compute anything new. Of course, there is an important computations that you need to do for G and H matrices, system and input matrices, but output equation is not changed if you're not changing your definition of output or type of measurement. Of course, instead of sampling the states, if you come up with a new discrete time state definition, you may also need to change C and D, but if you are coming from state space perspective, if your plant is given in state space domain, and if your goal is to obtain a state space discrete time structure, this is the best formal and easiest way of computing the state space approach. And in my opinion, this is one of the most important topics of this class. I will ask in the final midterm, I will ask in the final. Okay, I ask this everywhere, like PhD qualification exams, and everywhere I ask about the digital system question. I try to ask a question from this part. Okay, so in the next video, I will solve a simple example to better understand how we can adopt this technique to discretize continuous time plans in state space domain.